of PK3 means a different specimen. But anyway, they show well. And also cyclic one. This purple line is an experiment. A cyclic shear test was conducted. And yes, this colored one moving line is a numerical simulation result. So under shear cyclic loading, we could simulate the macroscopic behavior well. And yes, we examine the internal curve as well in this research. But anyway, we can simulate well. And also other specimens with different loading, different reinforcement ratio in X, Y, X, Y. The ratio are different. But in all cases, simulation is a blue, yellow line is the good agreement result we can obtain. And also we checked the changing of the principal stress strain directions. So good experiment give us very detailed phenomena, means how the stress direction changes after the cracking also was observed or measured. And then simulation, of course, we can check the changing of the principal stress strain directions. How is the angle changes? Yes, we can confirm by the simulation and dot line experiment. Yes, other detailed things also happens. And yes, one thing that is interesting was that after, yes, when we arrange the reinforcement with different ratio, after the cracking, the anisotropic stress field give us the big sliding of the crack. Shear sliding occurs. So as a result, when we just measure following the initial principal stress direction in compression, the very big reduction of the compressive strength is observed when we just follow the first principal stress direction in compression. So it should follow that just experimental result or model. However, after the cracking, yes, after the cracking, we have an isotropic stress field, and we have the crack, and yes, compression stress is applied. The sliding occurs on, yes, the crack. So slippage, the slip of the crack is very significant. As a result, when we just measure the stress-strain relationship on this line, it's observed or measured stress reduce significantly. So it is because we have a crack in a certain angle that reduce the compressive strength. So this kind of thing also, yes, this is a circle one is the experimental result, and this colored one is a simulation result. This could be observed. And it's actually, this can be done when we adapt the multidirectional fixed cracking model. So if some researcher adapts the rotational cracking model, it cannot be observed. So anyway, we did the panel test with RC. So finally, I show you just in 1 minute the beam test. So beam test also we did, and that was done by Kajima Corporation experiment. But anyway, we could simulate the beam test as well, and we can see the strain profile during the test. I would say yes, this is almost final. This is a case of RC, not HPRCC. When we apply the load, the crack is localized here and here. This is a typical cracking pattern of the case when we use just reinforced concrete. But when we use the HPRCC, HPLCC can have many multiple cracking. Therefore, the cracking region or strain region widely developed in the shear span ratio. This kind of different phenomena also we could simulate. So, okay, this is also the result. Anyway, yes, in case of HPLCC, we have many cracks distributed and in the simulation as well. So, in case of just RC, we have, it's not so easy to identify the cracking in the experiment, but just RC, we have this kind of cracking pattern. But different cracking pattern can be simulated. But anyway, this kind of thing can be done after we have modeled the HPLCC in compression, tension, and shear, and they are incorporated into the FEM simulation models. So that's all my presentation. Thank you very much for your kind attention.
Thank you very much. มีคำถามไหมครับ Any questions or comment to the speakers? จะเกี่ยวข้องนะครับการวิเคราะห์โครงสร้างที่ crack นะครับแต่ว่าใส่เส้นใยลงไปนะครับก็เกี่ยวข้องกับความทนทานของโครงสร้างแน่นอนนะครับเพราะว่าเมื่อมีรอยร้าวเกิดขึ้นแล้วนะฮะเราก็จะต้องวิเคราะห์มันให้ได้ไม่งั้นก็จะไม่สามารถคาดเดาอายุของโครงสร้างต่อไปในอนาคตได้นะครับถ้าเราไม่สามารถวิเคราะห์โครงสร้างที่มีรอยร้าวได้ The last speaker came from Tokyo Institute of Technologies Assistant Professor Matsumoto Koji he got his bachelor, master, and PhD from Hokkaido University. He doing the research on many fields on concrete structures. Today, his topic, I believe, okay, maybe you can show, okay, you can introduce yourself. Microscale analysis for deterioration of mortar subject to mechanical actions. So please, Professor Matsumoto.
Thank you. Thank you for kind introduction. My name is Koji Matsumoto from Tokyo Institute of Technology. Today's my topic is actually I did in the Hokkaido University, so I put, in addition to my name, but I put my supervisors, Dr. Yasuhiko Sato sitting there and Professor Tamo Ueda. Anyway, today's my research topic is mesoscale analysis for deterioration of mortar subjected to mechanical actions. Maybe most of you are difficult to imagine what is a deterioration subjected to mechanical action. So firstly, I would like to explain what the deterioration due to mechanical actions of concrete. First of all, what is the definition of the deterioration? In my opinion, the deterioration is the degradation of the material properties or structural performances over time, which causes as time goes on. So maybe you can imagine that as for the deterioration of concrete, you can imagine chloride ion attack, alkali silica reaction, frost damage, or drying shrinkage, and so on. They are caused by the environment surrounding the structure, so-called environmental actions. But not only these environmental actions, there are other factors which induce the deterioration of RC structures, so-called mechanical actions. The most typical mechanical action is fatigue loading. And these pictures show the crack propagation of RC slab under the fatigue loading. So you can see that at the initial stage, many cracks happened and they become wider, and finally the spalling of concrete happened. So this is one of the deteriorations due to the mechanical actions. So okay, yeah, fatigue is one of the most typical mechanical action which causes deterioration of concrete structure. So in current design method, how it is treated? Okay, in the most of the design code in all over the world, the fatigue design is done by SN curve and Miner's law. So what is SN curve? SN curve is the relationship between applied stress level, okay, this vertical axis, and number of fatigue cycles when the failure happens. So by using this relationship, if the stress level is given based on the design load, we can specify the number of fatigue life cycles. Then, what is Miner's law? Miner's law is used for fatigue loading, which magnitude is varied over time. But anyway, by using this equation, again, we can determine when the fatigue failure occurs under certain stress levels. However, they can specify, by using this method, we can verify the safety of the structure. But by using them, it does not give the degradation process itself. And also, performances other than fatigue life is unknown. Again, this is a concept of the how do we consider the process of maintenance of the RC structures. As for the performance-based design concept, there are some kind of performances, structural performances. One of them is safety, and maybe the strength can be one of the index for the safety verification. This graph shows the vertical axis is strength, and the lateral axis is time. At the at the beginning, this blue line is the actual strength of the structure, and this pink one is a required level of the strength. At the beginning, of course, the actual strength must be higher, larger than that of the required one. Then, due to the deterioration, this blue one decreases like this. Then, if the blue one reaches to the required value, we have to repair or strengthen this structure to maintain this structure. And also, not only the safety, but also we have to verify the, for example, serviceability or durability of the structure. Maybe crack width may be used for durability verification, and deformation may be used for serviceability. Then, in the current design method for fatigue, it is like it gives only this point when the failure happens. As I mentioned, the process is completely unknown. It means that the shape of this curve is unknown. So it means that we cannot verify how much strengthening or how much repairing is needed for the structure. It's one of the problems. And also, the current fatigue design is only for safety verification. So how to verify durability, how to verify serviceability, it's completely impossible. In other words, it is like current design method for fatigue is still allowable stress design. It's not applicable to the performance-based design concept. In this slide, I want to explain the concept of the mesoscale analysis, but maybe you already know by the presentation by Dr. Sato. But definition of the mesoscale analysis is like the target size is a bit smaller than the member size of the concrete structure. In member size, we often conduct the FEM analysis, right? then in this FEM analysis, constitutive law of the concrete is a stress-strain relationship of one element of concrete. Right? It means that we assume that this concrete element behaves homogeneously. Right? However, actually, concrete itself is a heterogeneous material because it is composed of aggregates and mortar. So, in this mesoscale, we treat this concrete as a heterogeneous material so that it's composed of aggregate, mortar, and sometimes we divide it into maybe different components as well. So by using this concept, in the real structure, actually, not only mechanical action, but also mechanical actions and environmental action are acted at the same time. And as Professor Nakamura presented today, the environmental action and mechanical action is not independent. They affect each other. So, in this presentation, I did not consider this environmental action, but in the future, we have to introduce the environmental condition as well. In order to do that, this kind of mesoscale analysis is very useful. Okay, so the target of this research, target of this presentation, okay? This presentation purpose is to develop the mesoscale numerical modeling of cement-based materials. In this presentation, it is mortar, okay? Subjected to various time-dependent loads. The various time-dependent loads contains like creep load, or of course fatigue load, and a seismic load, and impact load as well. And maybe you know already this one, but I want to briefly explain this. Method of analysis is rigid body spring model, or RBSM. The analysis object, it is mortar in this study. Analysis object is divided into these random shape elements by the Voronoi diagram. And in the RBSM, element itself is a rigid body, so there is no deformation, but springs are interconnected like this. And there is two directions, which is one is a normal direction and shear direction like this. So to model the time-dependent behavior, the point is how to model the constitutive law. Okay? Since I treated the time-dependent behavior, the constitutive law must be the stress-strain time relationships. Or in other words, in this constitutive law, stress is determined by the strain history. Okay? Not only strain, value of strain itself, also time affects the respondent stress. Okay? Then, because of the time limitation today, I cannot explain in detail for this, but the basic concept is this. Both in normal and shear direction, this mechanical model is introduced in my model. This model is composed of 4 components. Okay? First one is elastic strain. The other is viscoelastic strain, viscoelastic strain, and the last one is cracking strain. Okay? And each component represents the the material, one of the part of the material in the microscopic level. For example, elastic strain represents the deformation of the aggregate and also the cement, hardened cement paste. And the viscoelastic strain is the, since the elastic spring is connected here, it is reversible strain, but it is time dependent. The time dependency is represented by this dashpot element. And then third one, viscoplastic element is composed of slider element and dashpot. So it represents the eye.